I'm Junichiro Makino from Kobe University, and I will today briefly describe our current project on the Fugak acceleration. Well, I don't quite remember the full name of the program. The project is towards a unified view of the universe from large-scale structure to the planets. And my talk will be organized roughly as follows. I'll start with the goal and overview of the project and the structure, and then I'll overview the current status of the project. And currently, our project contains four sub-projects from the large scale to the small scales within the universe and planetary science. And I briefly overview each of them. And finally, I would like to say a few words on our experience in using Fugak and why and the consequence of them. So here is how our project is. The goal of our project is basically to try to construct a holistic and unified understanding of the formation and evolution of the hierarchical structures in the universe by combining the material estimations with the latest observations. So that means actually we really try to model the largest scale of the universe. This is the cosmic microwave background observation, which basically shows how the inhomogeneity of the universe in the very early stage, and from these inhomogeneities the large scale structure of the universe and the clusters of galaxies and galaxies have been formed through the gravitational instability, and within the galaxies the small scale instabilities of the interstellar medium from the molecular cloud, and within the molecular cloud stars are formed, and one of the stars is of course Sun. And also within the galaxy, at the center of the galaxy, there are massive black holes which create and emit the emissions, and some of the stars go through the supernova and generates the heavy elements and feed them back into the galaxy. And around the stars, there are things like the protoplanetary disk, which in turn form the planets like Earth, like our Earth. And on the surface of the Earth, we of course have the surface environment, atmosphere, and in the interior of the planets, we have the mantle convection and things like that, which actually shapes our planets. So our goal is really to try to model the universe and the planetary system at all levels. Okay. So in order to achieve this goal, basically we are sort of trying to team up almost every important groups in the Japanese astronomy simulation researchers of science. As a result, we have the consortium of the 21 research institutes and the 97 researchers. And these are organized into these four sub-projects, starting from the large scale structure of the universe to the galaxies and the star clusters within the galaxy, and also for the smaller level, from the molecular cloud to stars and the planetary formation, and the sort of the separate subjects, but with the scales in the several different region is astrophysical phenomenon of the black holes and the supernova. This basically means that the very high energy and the general relativistic phenomena And at the last but the least important is the solar and planetary dynamics and evolution. So let me just very quickly go through what we are doing in the subject. In the subprogram A, we are trying to perform things like the dark matter halo simulation, and we also studying the impact of neutrinos to the large-scale structure of the universe using the Blasov simulation code, and we are also working on the galaxy formation with the star-by-star level resolution, and related down through the newly developed code of what we call as RIPS. And for the star cluster simulations within the galaxies, we also developed a new code where I forgot to put name here, but the P3 and Beta both use our new algorithm of particle twisting in order to reduce the correction cost from n squared to the n of n. And therefore, basically, most of these codes are ready, and some of the code actually have finished most of the scientific runs at this point for the project. And for the subject B, which covers the star formation and molecular cloud and the star formation and the planetary formation, for the formation of the molecular cloud and the global MHD simulation of the protoplanetary disk, the code is basically essentially ready. And for this one, we have actually modified the Athena++ code, which is developed by one of our group members and people in Princeton universities, and modified so that it used this type of UTOF libraries in order to achieve the communication between the multiple threads in the MPR process. And for the large-scale simulation of the planetary formation, we also developed a new code also based on the particle twisting. And for the last growth in the turbulent planetary disk, it is done through the direct Navier-Stokes simulation. And for this one, it is the 4K to the cubed particle flux with the 4K to the cube grid points. So for this one, the code is not ready, and the production run is having done. And for the subject C, there are again several codes for the general relativistic radiation MHD code and the high order MHD code and the particle insert estimation for the plasma, and also the post processing high accuracy general relativistic radiation transport code, and also the two different approaches for the supernova, and one is the first principle neutron transport in supernova, and the other is the traditional code with approximate treatment, but with a full 3D simulation of the supernova explosion. And all these codes are now working, and I will briefly discuss the results shortly. And for the subapproach D, the goals are to do the large scale of the solar convection layer simulation, which to reproduce the velocity structure of the observed sun. And for the Venus atmosphere, we introduced a more realistic heating scheme and perform the global non-hydrostatic model. And for the mantle convection, we try to model Earth and Moon using the full 3D code. And for the giant gas planets like Jupiter or Saturn, we will be able to do for the first time the global 3D-dimensional simulation of them using an inelastic rotating spherical shell approximation. And for this one, I just briefly first one, the solar convection. For this one, we have actually succeeded to reduce the differential rotation of the sun, which is determined through the solar seismology observation. And for the first time, using the simulation with the 5 billion grid points. And through this, we can declare that we have solved something called the convective conundrum, which has been the long-standing problem in the solar physics. And we also have further increased the resolution and the success in reproducing things that are reproducing better. And for the rest of the things, one important thing is the performance. For the solar convection code, the efficiency is around 10%, and for the spherical harmonics code, which is used for the Gaussian shell model, the achieved efficiency is around 40% on PUGAC. So here is showing some of the main results, and this is the snapshot from the simulation of the neutrinos for the large-scale structure formation of the universe, and this one have actually achieved a very good, weak, and strong scaling efficiency, and selected as one of the finalists for the Nobel Prize. And here's one picture from SAMP, which is the dust growth in the turbulent superprotonic disk. We have found up to the 4K to cubed particle flux in the 4K by cubed grid point direct Navier of the simulation. And so that means we have reached the Reynolds number of nearly 40,000 and achieved succeeded in collecting the very good statistics of the growth of the dust in the turbulent planets. And this is the comparison between the n-body and Grasov simulation for the neutrinos. The density field by Grasov simulation, and this is the n-body. And these are adjusted so that the computing time and the memory requirements are similar. And for the neutrinos, the Grasov simulation can achieve much smoother and results and much better effective resolution for the velocity structure for neutrinos. And for the main results from subproject C, we have achieved very good simulation of the observed M87 radio source over the central mass black hole, and our simulation helped the observers to understand the misalignment between the M87 radio source and the gamma ray sources. And for the sum, this one shows the sectional view of the rotation velocity. Here is it's rotating slowly compared to this region. And this is the observation of the real sum. And you can see that with the low resolution simulation, the velocity field is completely different. But as you increase the grid number, the overall structure is now pretty close. And you can also see that the slowly rotating area very close to the surface is now, which is visible in here, is now reasonably reproduced with a very high resolution models. Okay, so I'd like to spend a couple of minutes for the current status and the PUGAC issues, which is not limited to us, but sort of shared by all users. The question is simple. Is PUGAC easy to use? And the answer, what we say, is yes. And this is actually certain true. Compared to K, PUGAC is much easier to use since it has the standard ARM CPU and the standard Clang or the even R-CCS compiler, this is really very helpful. However, we have experienced that application actually runs on Fugaku, but rather slowly. The efficiency of the programs are fairly tuned on x86 falls typically by large factor, and the situation is even worse for the programs tuned for K. And this is true even after we have optimized the kernels using the SV and other stuff. And the essential reason is that there is the architecture difference between the Fugaku and, for example, the Intel Skype. The latency of the floating point operations and the cache are much bigger compared on the Fugaku, and also the out-of-order instruction window is much smaller, and the load store boundary is also smaller. And this results in the coding something like this. Fugaku cannot fill its pipeline for loops which actually showed very good performance on Xeon. And this is just one example of the gravity and the electrostatic interaction between particles. On K, where something like 75% efficiency was possible, and on Skylake, we could still achieve something like 60%. But on Fugaku, if we just use the SV intrinsics, even after everything is written in SV, the efficiency was pretty low. And you can improve it to something like 25 or 30% with things like using the techniques like loop efficient and step learning and other stuff. And for this particular case of the gravity, it is not impossible to achieve something like 50% by minimizing the number of the instructions in the loop through the manual rewrite of the compiler generated code. And this is done by Kevin that year. So compared with K, the latency is much larger, and the number of architectural registers is too small for the compiler to achieve the good efficiency or for any human beings to write good code. So you can guess why this happens. Basically, the design is not maximize the floating performance within the power and the asset budget. And the result is quite impressive, not too far from the initial numbers of the NVIDIA GPU for the watt performance number, but this is not achieved for the general application. So we sort of knew that. And so the question how we can use Fugaku efficiently, and one possibility would be try to use iterate everything using the gem. And the point is that we have thought it's probably impossible to fulfill the three goals at the same time: the performance and the range of high efficient operations and the compatibility. And the Xeon has, and if you compare Xeon and GPU and Fugaku, each has lacks one. So this is the end of my talk.